Hello, everyone, and welcome to the Geek Narrator podcast. I am back with another topic, another very interesting episode. Today, I have Nitish from Parseable, and Parseable, which is a observability platform that gives you fast and highly scalable solution for your observability needs. So, we are going to learn about Parseable, why it was created, and how does it work, its architecture, some of the key components, some internal optimizations, and some future advancements. So, welcome, Nitish. I'm really happy to have you. And let's start with a little bit of introduction, and then we can dive into Parseable.
Thank you so much, KV, for having me. It's a pleasure being here. I've been a follower of the podcast for a while, so uh, great to be here. So let's quickly go over the background and why did I start Parcel, right? I started my career as a developer here in India, and I thankfully got into open source quite early. uh, After my initial stints, I got into this company called Minayo. It's an open source S3 compatible uh, object storage platform that actually they're doing great right now as well, right? So I got to be one of the early developers there, and then once I started working there, I also got to be in front of a lot of customers, a lot of users. And one of the common patterns, like the recurring patterns was, and even early on, like around 2020, 2021, one of the very common patterns was most of the people wanted to bring workloads on S3 or object store where it involved smaller files. And these
Hmm.
smaller files are essentially JSON files with what few KBs. And but who was generating these files, right? So it was either some sort of observability workload, or it was some sort of OLAP workload where they're capturing events and then sort of wanting to store on S3. But if you look at the S3 API, it's not built for small files. S3 API is built for bigger chunks. So you have get and put. You can't really see inside a file, and then there are also problems around how do you organize data on S3 if you have millions of files in a single prefix. It's going to cause a problem. So that pattern kept repeating, and then that's where it felt like a great opportunity to build something on top of S3 or object store that allowed people to handle smaller files at scale. Now that's the early story, right? And then we started Parsable around 2022, and that's how it started. And then we sort of kept iterating, and we landed on observability as the core challenge today.
Okay. That sounds like you have faced all these problems with the S3 API, and then you figure out that probably there is an opportunity to solve this problem. I'm curious, why observability though? Like, how did you stumble upon that?
So if you look at the ecosystem today in observability, right? So you have a lot of traditional databases. For example, you have Elastic, you have Splunk, also sort of based on Lucene, but not much work has gone into building something from the core. A lot of people are now adopting ClickHouse as their observability backend, but
Hmm.
ClickHouse is essentially an OLAP platform that
Yeah.
also allows you to update stuff. That also allows you inserts, upserts, and stuff like that. But looking at the just the observability use case, the data in observability is immutable,
Hmm.
and it's almost like a system of record that you don't want to change.
Hmm.
And which means the observability database can actually be much simpler because you don't want to allow any sort of modifications of data. So once data
Hmm.
is written, you just want to look through that data, right? You don't want to modify that data. You don't want to edit any sort of event, right? So uh, that means that if you actually start building an observability database from the scratch, the first thing is no upserts, no inserts, and that actually allows you to remove a lot of complexity that you see currently in let's say other databases which are OLAP but being used as
Hmm.
observability systems. So and that sort of led us to actually build a system that basically is append only. You can always keep adding stuff but never edit stuff, and that helps us remove a lot of complexity around observability. ecosystem, and then sort of help us build a scalable system that just does what it needs to do, nothing extra.
Yeah. I think that's a powerful idea, to be honest. Like I was also talking to some other database folks, and when you really want to specialize for a domain, you can actually simplify a lot because you understand the trade-offs. You understand some decisions that you can make, what a general database cannot make because they want to support wider range of solutions and wider range of workloads. But when you understand observability, as you said, it's an immutable system of record, so you don't need any upserts, you don't need modifications, so you can probably trim down all those features and create something simpler, very much focused on observability. So that's a powerful idea, and I'll probably come back to that idea a bit more while we are talking about it. But for now, I think let's talk about like the key features. So okay, so we have a database. We know it's for observability, it's immutable, and it's much simpler, built on top of object storage and so on. What are the key features though? For example, if I am a user and I want to learn more about Parsable, why should I even care? What are the top features that you would like my attention to?
So the other sort of decision that we are taking, right? So because we're building a database from scratch, we want people to deploy in their infrastructure, and we have seen people struggle with Elasticsearch quite a bit. It is one of the most operationally heavy systems out there, right? So one of the key design discussions or design decisions that we have taken is basically simplicity comes first, not only in the architecture but how you deploy stuff, how you run stuff. So uh, so there's zero dependency in the system. So Parsable is shipped as a single binary. There is no external metadata database needed. There's no external, nothing else needed actually, just the object store. So you point the Parsable binary to a bucket on your object store, and you're set. That actually allows you to sort of get up and running very quickly. You actually see value very quickly on your with your observability data, and you have just fewer knobs to turn. So that is one of the key angles that we have taken, the zero dependency. The other, I mean, before we go to the other thing, right? So zero dependency also allows you to run it on your system actually, and run it on your laptop. Actually try the system very early on and see the value before actually moving forward. The other important aspect is around indexing, and indexing is a touchy topic, right? So every database is supposed to index stuff because that's how you search stuff, right? But if you look at modern data ecosystem, if you look at some of the most performance systems, DuckDB, for example, does not do index,
Yep.
right? And then again you bring this problem in the observability space. So you start thinking, okay, you have OLTP, which is, let's say, a couple of terabytes of OLTP data is already huge.
Mm.
Then you come to OLAP, you have few hundred terabytes of data, huge. Observability, if you look at the data, it's like order of magnitude bigger than OLAP. For example, we were speaking to several customers who generate more than 100 TB per day.
Mm.
So observability is a big data problem with this signal to noise challenge, right? So you have lots of data, and you're supposed to sift through that data to find that few important lines. So that means that indexing everything is just going to slow your system down, slow your ingestion down, and it does just simply doesn't add a lot of value. So
Mhm.
we took a decision to actually be index free completely, and we'll come to how the search works. But system is basically index free. At the same time, we give the customer or the user the opportunity to actually decide what they want to index versus we deciding, we'll index based on, let's say, we'll index everything or we'll index based on certain labels, certain chunks. Instead of that, we are just saying that, you decide which columns, which data sets you want to index and for how long.
Mhm.
But other than that, the system does not index anything
Okay.
on itself. So the volumes are high, and the latency also gets better because we are just not indexing. You are able to respond to the client quickly that, okay, this batch is done for ingesting. So it improves the performance across the board. So that is the second interesting feature, that feature more than feature, it's a design angle that we have taken. The other thing is around API driven. So everything on Parsable basically works on HTTP. Whether you want to ingest stuff, whether you want to query stuff, it's all available via simple APIs, and that allows us to actually integrate with the ecosystem.
Mm.
Observability actually, one of the bigger, lesser talked about challenges in observability is you have just a wide range of data sources. You have log
Yeah.
agents, you have metrics, which basically is pull based model where actually you go and scrape stuff, and then you have traces, which is coming from something, some other agent. You have open telemetry actually picking up now, which they have their own set of agents. So the ecosystem is huge. There are a lot of tools, and one of the core aspects of observability is you want to unify stuff in a single system, which means this single system should be able to actually capture data from all these
Mm.
sources. Now, HTTP is one of the most widely adopted protocols, and we just made everything HTTP only, which or HTTPS only basically, which allows you to ingest stuff from almost anywhere.
Mm.
So that helps us move quickly in terms of, let's say, we see a user or customer trying to deploy Parsable, we are able to move faster, actually get them on board using the HTTP interface. We also support Kafka and other protocols, but uh, HTTP allows us to move faster in terms of integration. And
Okay.
finally, diskless design, S3 first design. So basically, when you actually, and we'll talk about this during the read, etc. also, but basically, when you ingest stuff, we write that data locally on disk, stage it for a small duration, and then push it on S3. So essentially, the design is like you don't want to depend on the local disk at all, and
Mm.
you can actually just push data directly to S3, so that you're just stateless on the ingestion side. This allows you to scale up and down as needed, as traffic increases or decreases. You're basically much more agile in terms of responding to traffic.
Mhm. That makes sense. And observability is so close to my heart. I work as an observability and reliability engineer, and I deal with all these problems that, like you mentioned, signal to noise. The volume of data, and the variety of data. So there's like velocity, variety, and volume, and all these three things create a lot of problems when it comes to the database. Unification that you talked about is another problem, because there are just so many resources that increases the footprint of your infrastructure, and the person who manages that infrastructure is a pain for that, right? Just to bring everyone on the same page, when we talk about observability, like as you mentioned, there are different types of data. You have logs, you have metrics, you have traces, you have profiles, and multiple other things. What is supported as of now? And the next question I want to ask you is, you said it's a single binary, but how does the deployment look like? So when I deploy my application, is it running in the agent mode, or my application has to write some HTTP client logic where I have to make HTTP calls and so on? So let's throw some light there.
So I'll take the first question first, right? So what is supported right now? Which kind of signals we support? So basically, any sort of log data is supported, and you can pick any format. And logs are basically they're semi formatted.
Mhm.
They're not very well formatted, and there's a lot of effort going on, especially open telemetry
Yeah.
is getting adoption, and actually there's standardization going on, but uh, there's just so much background, so much history in log, especially, that it'll take a while to actually standardize across a
Mhm.
certain format. But coming to what's supported, right? So we can basically ingest any sort of log data, any format, and we actually are able to identify certain formats based when you send that to Parsable. And identification allows us to actually separate out columns properly, and give you a better experience in terms of search. So any open formatted, or let's say certain format log data is you're able to ingest that. Open telemetry metrics, open telemetry traces are also supported. we are working on adding like Prometheus style scraping to Parsable. So basically, you can actually upload a Prometheus config, and we should be able to actually scrape all the targets as you want. But yeah, so currently we are working on the Prometheus style scraping. But other than that, any log format is supported: metrics, OpenTelemetry, traces, OpenTelemetry.
Okay, sounds good.
And coming to the other question, right? So which was
the deployments.
Yes. So basically, single binary is very easy to get started. So this is just a single command that you actually run, and on your laptop you are up and running. But let's say you want HA. Let's say you are going for a production deployment. You want to deploy Parsable in a way that it's resilient to, let's say, certain nodes going down, right? So that's where you have this the same binary. You can actually pass on flags to actually run them in certain modes. So there are 3 modes right now. One is your ingest mode, meaning this node will only ingest data at certain endpoints, and it will not actually entertain any other sort of requests. And the other mode is your query mode, where this node is just going to allow you to query stuff. And then there's third mode called Prism mode. Prism is our UI that basically integrates with Parsable. So the third mode is Prism mode, where that sort of acts as your main node or master node, which is going to allow you to use the front end, use the UI via browser, and interact with the cluster. So these 3 modes, and then there's also this indexing mode, where you can actually run the binary in index mode, and then this mode allows you to index stuff on demand. So you can actually choose that I want to index, let's say, data set X with columns A, B, and C for, let's say, a duration of last five days. So at any point in time, it will keep those 5 days worth of columns indexed, and it will keep sort of removing the older indexes.
Interesting.
So this is how you deploy, and then all these nodes are basically you are able to run them in a configuration where they don't talk to each other. They all talk to the single S3 bucket.
Okay. And how does it interact with my application?
So application meaning the application that's sending signals, right? The logs, right? So if, let's say, you are running this in HA, and you have an application that's sort of sending data, most probably you will have some sort of agent running on your pods or on your host, right? So let's say pick any common log agent, let's say FluentBit or Vector or Logstash or whatever, right? So almost all of them have HTTP out plugins, and that's all you need basically. So you basically configure HTTP out plugin to point it to the Parsable ingester or the load balancer, and behind the load balancer you have all the Parsable ingesters. So the moment you configure your log agent to send data to this ingestion node, that's all you need basically.
Okay, fair enough. So just to kind of do a quick recap, right, what we have talked about. So we basically support logs and metrics as of now, and
traces as well.
And traces as well. Sorry, I missed that. And then, of course, basically, you can deploy any agents that are available to you, and whatever supports HTTP out. And then you can deploy your parsable nodes in different modes, ingest and read only, and there was index one, and I think the other one was which I missed. What was the other? Prism. Okay, that's for the UI, right?
That's for
and then UI. Okay, makes sense. And then your application can basically start ingesting data, and then you use object storage, so all the data goes into that. Okay, makes sense. Let's go a bit deeper, right? So as I am basically configuring my nodes of Parsable, like assuming this is all production, I'm not running like single binary. So there are multiple ingest nodes, there are multiple read nodes and index nodes and so on. And depending on my workloads, I'll have to configure how many of these I want and how many of the other ones. So first I want to talk about the isolation of these nodes, right? Um, when so what is the design decision when you kind of thought about isolating the reads versus writes? What are some key challenges that you faced there, or key improvements that you got?
So when you say isolation, do you mean like node
Isolation
should not?
between, yeah, the different nodes. So the node that is ingesting should not be serving reads and so on.
Right. So basically, the idea is if you isolate that, the benefit that you get is basically your failures are limited to certain domains. So let's say
Mm-hmm.
if a single node is down, you know that just the ingestion is down. It doesn't affect your query. It doesn't affect any sort of other operation. So that way, and people actually access observability systems when something is wrong,
Mm-hmm.
and you just don't want to give them that problem of, okay, the observability system is also now behaving weirdly, right? So you want to limit the failure domain, and so that was the main thought process behind that, right? But other than that, it also, you're able to actually choose the hardware properly. So for example, the ingest node is essentially network heavy. So because we are written in Rust, we are very efficient in terms of CPU and memory. So almost always network is the bottleneck. So for example, if you're running it in production, you can choose network optimized nodes for ingestion, but for query, we'll choose CPU optimized nodes.
Mm-hmm.
So that way you're able to actually choose better hardware for which is suitable for the job that the node is doing.
That makes sense. And that's like the typical benefits that we get from read write isolation, and makes a lot of sense, at least in the modern world. Let's start with understanding the ingestion process, right? So the first question I have is, why have the separation between ingest node and indexing node? Like, why can't the ingest node index my data as well? And we can go further into what happens when I ingest the data.
Right. So ingesting and indexing are again like different problems, to be honest, right? So
Yeah.
indexing is again a lot of CPU intense processing happens,
Mm-hmm.
and it's basically if you add that in the right path, you are going to sort of slow down the ingestion as well.
Mm-hmm.
So we decided that, and anyways, in our case, ingestion is basically, of course, non-optional, but indexing is optional. So you can choose to index, or you can actually choose to not run the index nodes if
Yeah.
you see the performance up to your thresholds, right? So that way, it made sense to sort of separate them out, and then again, the index node configuration will be a little different compared to, let's say, ingest node. Now coming to the ingestion process itself, right? So it's relatively simple. Basically, simplicity is at the core, right? So what we do is, the moment you receive a HTTP call, right? HTTP call with a payload that is a big JSON. So when you're sending stuff to Parsable or to the ingest endpoint, you're basically sending a big JSON payload, which has data in any sort of format. And now there are two ways where you can actually ingest. One is where your data set is dynamic, which
Mm-hmm.
means that we meaning the server doesn't care about the format at all. So let's say in the first call you send me three rows with let's say columns ABC with different data types. And in the next call, you say send three different columns. You send XYZ
Mm-hmm.
and with again different formats. Server will still be able to ingest it, and in the UI you are going to see ABC and XYZ, and ABC will be uh, basically present for first three events. For next three events, XYZ will be present, and there'll be nulls otherwise. So
Yeah.
this gives you a lot of flexibility in cases where you don't know the format very well.
Mm-hmm.
uh, and this is where we have seen a lot of organizations actually suffering because they didn't decide on a format early on, and now there's just a lot of momentum to actually change stuff or change the formatting. So basically they want a way to ingest everything and just be able to query, not care too much about the format, not care too much about the log format itself. So but that has challenges, right? So that also adds a little bit of slowness, because we identify the data set, and then we identify the format, we identify the data type, and then once we identify all that, we are able to actually make sure data types are correctly marked for each and every column. But there are chances that, let's say, we identify a data set which is a timestamp as a string, right? So this is not foolproof, right? So the ideal scenario is a static data set, where you actually send us the format first. You tell us that this is what I'm going to ingest, and then you basically send events that is in that format. And in this case, we reject events that are not in the format that we agreed upon early on. So this way, you have this flexibility of using a dynamic data set, which is basically free form, send anything. And then you have the static data set, where it's a more matured setup, where formats are clearer. So this is the ingest side, right? So first of all, this is how you can send. Once we receive the data set, once we receive the event, and this event is essentially a big JSON payload, we parse that, we convert it into something called Apache Arrow format. Apache Arrow is gaining a lot of momentum now. It is one of the very well designed in-memory formats. It's heavily compressed. It allows movement of data very. It makes the movement of data very easy. So we can convert it to this Arrow format, and then we commit it to the local ingestion disk. And the moment we commit it to the disk, we respond to the client saying, hey, your ingestion is done. But this data is still not, let's say, you could lose that ingestion node, you could lose that disk, and you might lose this data. So this is where this is a design decision, but basically this is where we recommend that you should use a small but persistent disk on your ingesters, so which allows you to make sure that you're not going to lose this 1 minute worth data. If let's say you had a catastrophic failure, and your node is down, but so for example, if you're on AWS, we'll probably recommend EFS on this ingestion node. That way you're making sure that even if the node is down, you're not losing this 1 minute worth data. In some cases, it's actually fine to lose, let's say, a few minutes worth, but in some cases it's non-negotiable. So depending on how your basically failure threshold is designed, you can choose to run EFS on the ingestion node, so that way you don't lose data. But so let's say you are running EFS and you have this ingestion node, data comes in, sits on your local mounted drive, and right till now it's not in Parquet as such. It's basically in a arrows format. And after a minute is over, so let's say every minute bracket, we run a async job that basically converts this arrow file into something called Parquet file. And Parquet is where it's a very well-known format. It actually allows you to compress data heavily, up to 85% is without any tuning. You can expect 80 to 85% of compression. And then this compression, basically this compressed format is then pushed to S3. At this point, after a minute, your data is committed to S3, and then it's stored in S3 in a certain prefix structure. But basically your disk is again empty. So this local data is cleared, your disk is empty. So you don't need a huge EFS volume attached to your ingester, but you need just enough to make sure that staging data is safe. So that's the ingestion flow.
Makes sense. And you mentioned Arrow and Parquet. I mean, we did a podcast with Andrew Lamp and talked about FDAP, and it's really promising, and a lot of database are using this stack. So viewers and listeners, if you want to check it out, you're free to check it out. Coming back to the discussion, I think it's very reasonable. It makes sense how you do it. I just have one question. So you talked about the tuning properties, right? If I want durability, I can basically tune it so it can, have this storage and different types of storage, so it's all replicated and so on. On the other end of the spectrum, I can, if I don't care a lot about durability, I can basically say I want diskless setup. Is that also a possibility? Like if you buffer everything in memory, I mean, technically, if there is something catastrophic happening, I can also lose the data. Same with disk. So can I say that I want diskless setup and I just write to S3 after a batch size is filled in memory?
So that's definitely possible. We don't, as of now, support it. Basically, what what we can do is keep this in memory and just flush to S3 directly. So really diskless. It's not supported right now, but that's a small change that we can actually do it. Either ways, even if there is a disk and you don't care too much, basically you can use in for example in Kubernetes world you can use something called ephemeral storage that actually just is just there to just for the OS to flush stuff, but it doesn't it's not like retained across restarts or anything.
Mm-hmm.
So as long as you don't care whether it's on disk or on memory, you should be okay.
Okay. This question is basically coming from the architecture of Warp Stream, which is recently acquired by Confluent. And it's like zero disk or disk free architecture. And it's really useful because then of course, you only have 1 minute of state stored on your disk. So it's not a huge amount. But for something like streaming, probably it can mean a lot. And scaling becomes easier when you have diskless components. So that's the reason I asked this. And it's good that of course, it's a possibility. But what are the trade offs, right? Depending on, I think it boils down to the number of queries I'm making or calls I'm making to S3 versus the storage I have on my nodes, right? So what exactly I'm tuning for? So I guess it's the durability that I get if I have local disk, but they technically have the same failure modes, assuming the machine dies, the disk dies, and so on. So as a user, what exactly I'm tuning between?
So this is a very interesting question, right? So what exactly are you tuning for? Again, it depends a lot on the use case. For example, streaming, there's just continuous stream of data, and volumes probably are not as same as huge as observability. So in that case, you can keep it in memory and probably just flush directly. You lose it, right? But here the thing is, if you let's say allow direct push to S3, you're probably going to make uh, tens of thousands to probably hundreds of thousands calls to S3 per minute and from per ingester node. So that actually is going to just add to your S3 cost without actually giving you anything. You're basically going to fill S3 with millions of small files,
Mm-hmm.
and which is not really useful. And again, so for example, if you look at our architecture, do you want to convert every event that we receive into Parquet and push that into Parquet? So you're not going to get also the compression benefits,
Mm-hmm.
because the smaller the event, Parquet doesn't do a great job if you have a small event that's converted into Parquet, right? So the larger the Parquet file, the better compression benefits you're going to get. So that way, I think, especially in case of observability volumes, it makes sense to actually stage data for a bit, because otherwise it's just going to fill up the disk with very small inefficient Parquet files. Doesn't serve anyone very well, right?
That does make sense. Of course, you can always buffer data in memory and then send large batches. Um, and
Yeah.
yeah, I have two questions. So one, in the introduction, you said that S3 API is not well tuned for small files uploads, but are you getting rid of that problem by staging this data and creating large enough file, or how are you solving that problem? Have you done any customization there?
So basically, we still use the standard S3 API in the background, but because of staging and the way we handle querying, the way we handle staging,
Hmm.
we deal with the S3 API in a way that's efficient for S3 or object store. But that
Hmm.
so basically we make sure that observability use case is handled on our side, and then we make S3 calls in a way that's efficient, not only from the cost perspective, but also from a way so that data is well organized in S3. You are able to
Hmm.
actually query stuff efficiently, and you're not just overwhelming S3 with just millions of smaller files. So that's the translation that we do, and sort of ensuring that it's done in a manner which is optimal for S3.
Yeah, that does make sense. Talking about the S3 format, we talked about Parquet and why you use it, because it's supposed high compression makes it cost effective as well. How is data like organized in so I have buckets, right? But let's say I have like different services, and of course I don't think that granularity is supported, or it makes sense to support it. But how is data organized, and how is it partitioned in terms of buckets in S3, and tell us a bit about how that is organized.
So a single parsable instance basically points to instance or a cluster points to a single S3 bucket, and this bucket basically becomes the location for everything that's related to parsable. Inside the bucket, you have all the metadata that we store for for RBAC, for user access control, for per stream information, retention information, alerts. A lot of metadata gets created, but again, this is all stored on the bucket. And then after the all the metadata, you have these prefixes based on the name of datasets. So data is logically organized in Parsable as something called datasets. And then when you actually query the Parsable server, you basically use dataset as your table name. So essentially, when you write a SQL to query, let's say dataset X, you're going to write select star from dataset X. So that becomes your table name. But basically, coming back to the S3 format, you have these prefixes which are dataset names, and then inside those prefixes you have date, month, year. Basically, so starts with year, month, and then timestamp. And then inside those timestamps, you have all the Parquet files created by all the ingesters for that minute. So that way, when you are actually querying, you're already very well aware of where should I look for my data when you're querying. So you don't have to scan the S3 fully. You don't have to scan the bucket field. You know which time range you're looking for. So you're able to really narrow down the files that you're going to actually scan. So that's that way, and this also makes sure that we are not again filling a single prefix with a lot of files. So per prefix we have few files that basically are heavily compressed, and then we look at, let's say, few hundred prefixes per query. So that way this is well balanced, and it allows you to, again, it helps in the query optimization.
Yeah,
So
I
we
think that.
also actually,
Yeah,
go
go
ahead,
ahead.
please.
No, it's fine. You go ahead.
So now I think basically we are looking at adding like support for Iceberg and stuff. We still see some interest from users where Iceberg might be useful. So we might actually add that as well, and that allows you to, that opens up another aspect where you can actually use all your analytics servers or analytics engines to use to look at your observability data with zero changes.
Yeah,
That's
I
another
think.
angle that we're looking at. So think of this format that we store very similar to Iceberg, but just that we don't need inserts, we don't need upserts.
That makes sense. So I think it's again a standard way of storing things in S3. You mentioned about metadata though, right? Like there are data sets and metadata about, your RBAC and, alerts and so on. When is this metadata generated, and who creates it?
So all of this comes from no users. So let's say you create a data set, you started ingesting, and then you decided that, hey, I don't need this for forever. I just want like last 10 days worth data. And then rest of data should be just deleted or maybe archived to Glacier and stuff. So then you decide to set retention. Now this retention is stored as metadata on the Parsable server. Similarly, let's say you decide that I want to set an alert if something wrong happens. So again, this alert configuration becomes a metadata for Parsable server, and it's stored on the same S3 bucket.
Interesting. Okay, that makes sense. I have some more questions, but I'll probably come back to it later. But let's talk about reads, right? So data is ingested. There is staging happening at each ingest node. You store it on disk, and then after a minute, it is flushed to S3. And then it is, divided based on year, month, and, day, and then timestamp based and hour based, I guess. And then you have Parquet files, highly compressed, all of that, all good stuff. Now, let's say I'm reading my, I'm making some queries based on this data set. First of all, as a user, how do I know that what data set my logs are going into? Is it also a configuration that I have to provide?
Yes. So when we discuss about the HTTP call with the JSON payload, right? So
Yeah.
when you make that call, you actually also add a header in your HTTP call, which says which data set you are targeting.
Mm.
So and then there's also this data modeling angle that how do you think when you're, let's say, coming from Elasticsearch, you're coming from Splunk, how do you think of creating a data set? When should I create a data set? How should I logically separate out stuff? So all that, I think we can come to that later, but basically, let's say you decide that all my namespaces in a Kubernetes cluster, each namespace maps to one data set, let's say, for this discussion. So let's say you decided that namespace A becomes dataset A, and so on and so forth. So once that happens, now every service in your namespace A is basically going to send events to dataset A. And so once that happens, you basically receive everything in your dataset. And then you're, let's say, debugging something. So you're debugging a service called service A in dataset A. So you'll start with show me everything in this data set where application equal to or service name equal to or service name like service A. So that's how you start querying. And when the server receives this query, it's a standard SQL parsing. So we parse the SQL query, we create the logical and physical plans, and then that's where a little bit of parsable specific stuff happens. So we also have min max index. Basically, this is a way to organize stuff in a way that we know for each column, uh, certain file has what is the minimum value, what is the maximum value. So let's take it from the top, right? So you got SQL query, you got the response, you got the SQL query, and then once you got the SQL query, create the logical physical plans, and then we look at this data set specific metadata, and we look at the time range for the query. So when you make a query, you actually also specify the duration for this query. So you specify a start time and an end time.
Yeah.
And this query is basically going to look at data files within this time range only, because again we are dealing with huge volumes of data, right? So and observability use case essentially are always time bound. So it's basically, it makes sense to add this start and end time, and then once you start add this start and end time in the query, we now know which files to look at. So coming back to the SQL parsing, so you have logical plan, you have physical plan. Now you also know roughly which files I'm going to access, because the prefix is organized as timestamps. Now we take our internal metadata and we look at which files contain events from this service. So this is actually contained in the metadata itself. So you don't have to. So we have still not hit the Parquet file, or we have still not basically gone into Parquet files. We are still looking at internal metadata and deciding that, okay, I just need, even if let's say the time range says I need to look at 100 Parquet files, metadata has further narrowed it down to 20 Parquet files. So now we make get range calls. So still we're not actually downloading the whole Parquet. We make get range calls to those specific Parquet files, download the footers, and then start streaming the response. So then we decide that, okay, let's say these 5 events are actually matching. We send that, and then and then keep responding with further entries as we find them. So that's the high level flow.
Makes sense. That makes sense. So in a way, the metadata or is some sort of index, right? Like where you're
Yes.
able to narrow down like what Parquet file or what kind of range I'm talking about. So yeah, that does make sense.
And
And
then additionally, I think one thing we didn't discuss, right? So there's also caching. So
yeah.
because data is on S3, in many cases, uh, you want a certain sort of tiering between your, in your observability data. So you want hot data, recent data, like quick response, and then you're fine with the tail latency of S3 for
Hmm.
older data. So you can actually enable caching on the query nodes, and then query nodes basically don't even go to S3. They look at
Hmm.
the data locally, and then they can respond very quickly. So if you have cache enabled, the performance is very good. So in that case, you're looking at a response which is very similar to, like, say, a DuckDB or a ClickHouse, because it serves locally.
Mhm. That's fair enough. I mean, I was about to ask, do you also cache the data? But yeah, thanks for answering. Um, so this makes sense. I've ingested my data. Read queries also, fine. Um, Again, I have multiple questions, but I'll probably start with why SQL, for example. Like, uh, so I know a lot of solutions support SQL based. A lot of solutions just support like random, free form queries. Um, I like SQL, to be honest. Like SQL is everywhere. People know SQL, so it's not a problem. But in some cases, or let's say 80% of the queries that I'm making are not really complicated. I just want to look at a service. So I just say service this, and then probably time range I'm already selected, and just some random error message or something like that, right? So in that case, SQL might be a bit, you know, uh, over, how do you say, over engineered for the user. So uh, is SQL supported? Only SQL supported, or there are some other formats as well?
Yeah, no. So we understand, right? Look, SQL is very good, very well
Yeah.
adopted, but uh, a small group of people really like to write SQL, but the larger group doesn't really, want to write, right? So,
Yeah.
so the UI, actually, the parsable interface, or Prism as we call it, actually allows you to filter stuff without any knowledge of SQL. So you don't have
Hmm.
to really know SQL. The interface that allows you to filter, that doesn't use SQL. So you can actually simply, do it in a way that you're used to. For example, just select the service name, select the operator, and select the value, and
Okay.
and you're done. You don't have to really deal with SQL. But if you're a power user, you want to use SQL to slice and dice. You have a SQL editor where you are just free to do whatever you want
Hmm.
with your SQL knowledge.
That's interesting. Cool. I think this is fair because sometimes I don't like to write SQL. Sometimes for complex queries, SQL is way better. So supporting both is good. And I think now I also understand, the isolation that you have. So ingesters, readers, and then also Prism, sorry. And that is also isolated because I know how many of my users are going to use the UI, how many of them are, automated HTTP calls, reading, and so on. So that does make sense. You also mentioned that so logs, metrics, and then traces, right? So you also support traces. Usually, what I've seen is when you have traces, you also want to, correlate them with the logs that were happening, right? So I have a trace, but what happened in the logs? I want to look at that. How does that happen, and how does that change the data organization in S3, or it's taken care at the read time?
So when you do, so it doesn't change a lot during ingest or write time. Basically, it's on the read time. SQL has built-in,
Hmm.
mechanism to do,
Joins.
correlations. So giants is the way, right? So basically,
Yeah.
you have two data sets. One is your, let's say, a log, and then other is your trace.
Hmm.
And because I'm assuming this is open telemetry, and then if you have open telemetry, you have these IDs to correlate stuff. So
Yeah.
it becomes very easy, right? So you basically correlate using this ID, and you're able to actually see all the logs related to certain ID, all the traces related to that ID. and then it's just the UI's job to show it properly, so it makes sense. But it comes naturally to SQL.
Mm-hmm. That makes sense. And talking about like the failure modes, right? So we know. I want to talk about indexing, but as you said, it's mainly on the user side. If I really want to do it, it's optional. So I want to talk about the failure mechanisms first, right? So you mentioned that the like all the ingester nodes talk to a S3 bucket, and then they have this each of the data that is written by each ingester. What happens when an ingester dies? What happens to the Parquet file? What happens to the data written on the local disk, and so on? How do I get a new ingester? Like what changes in my architecture?
So depending on where it's deployed, so it changes a little bit. I'll, for example, this for this answer, I'll assume that this is Kubernetes,
Yeah.
and you have ingesters, and then you have a load balancer basically in front of all these ingesters.
Mm-hmm.
And assume you have 5 ingesters running, and then you have this simple load balancer round robin that's sitting in front of ingesters. Now the agent is pushing, or all the agents are pushing events to this load balancer. Load balancer
Mm-hmm.
is sending this data to ingesters in a round robin fashion. All good. Now let's say ingester one dies, and now the way, let's say we assume here that we don't want to lose data, so we have used a PVC. We have used a persistent volume claim and a persistent volume to actually store data locally on the ingester. Now this pod goes down. Kubernetes will see, because this is a deployment. This is not a stateful set. This is simple deployment. But Kubernetes will see that, okay, my pods are not the number that I want them to be. So it will try to spin up a new pod, and it will try to map the same PV to this new pod.
Mm-hmm.
The moment this happens, the new pod comes up in probably a different node.
Mm-hmm.
It comes up and it sees that, okay, I have some data locally, and this data is arrows file. It's not really Parquet. So it'll attempt converting, the moment it starts up. It'll attempt converting all the local arrows files to Parquet file, and then it knows where to push them. So it starts pushing them to S3. So that way, the moment it starts up, it also starts a async cleaning job. At the same time, you're also free to send events. That
Mm-hmm.
way, it starts ingesting events, and in the background also clears up older data. Now, this older data is basically timestamp, so it falls into the right prefix on S3. So it doesn't gets added to your current prefix or current timestamp. It gets added to the correct timestamp that's basically organized on S3. So that way you're not going to lose any data if it's designed well, or if it's deployed well. If, let's say, this was, instead of a PVC setup, this was an ephemeral store. In that case, of course, you lose whatever was on that disk. So that's where that threshold comes, right? So what is acceptable in the customers or users infrastructure? uh, we need to plan it like that.
Mm-hmm. That makes sense. What I've seen in typically observability domain is the data can also be a lot spiky, right? Depending on
Yes.
the workloads and the time of the day or day of the week and so on. The number of users interacting with your system, or let's say you're running a job that is creating a lot of logs and so on. So it can be really spiky depending on the workload. Are there any special things done to handle the spikes well, such that there are no failures in the ingestion or even the readers?
So again, like assuming cloud native infrastructure or Kubernetes infrastructure, the way ingesters are designed, it's very easy to add a new one. You just change your deployment to, let's say, instead of 5, make it 6, make it
Yeah.
10,
Mm-hmm.
whatever, right? So, but even that is sometimes is not acceptable, but because you don't want to lose a single event.
Yeah.
So for that, we actually wrote a Kubernetes operator,
Mm-hmm.
which does HPA based scaling. It looks at CPU utilization on each ingester, and the moment it hits a certain threshold, let's say 80%, the operator actually deploys, basically creates a new deployment with this new number of replicas, and the application doesn't see a change. So application still sees the same service, still sends events to that same endpoint. But now behind this endpoint, you have, let's say, 10 ingesters instead of 5. So this Kubernetes operator basically, scales it out automatically without you having to interfere with the system. But if you're,
Hmm.
let's say, not using the operator, in that case, it's a simple change that you just update the number of replicas for your deployment.
Yeah, interesting. I think that that makes sense. I want to talk about a bit about like the load balancing that is happening on the ingester, for example, right? Because that's the decision point where you decide how you organize your data. So I'm just randomly throwing a question at this point because I'm just imagining that let's say you have an ingester, and depending on what data set it is consuming for, it might make sense for you to have the same ingester ingest for the same data set. So I'm pointing at partitioning of data based on data set, right? So does that help you, organize your data in S3 better to make reads even faster, or having it round robin is better because you don't have to have hot partitions and so on?
No, so I think I didn't explain it early on, right? So basically, when you send events to ingester, and ingester sees that, okay, this belongs to a certain data set, and the arrows file it creates is actually belongs to that data set. So it doesn't like club all the events from all the data sets in a single file. It actually creates separate arrows files for each and every data set. So that way there's already always partitioning, and then
Mhm.
it's actually much easier to now just convert Parquet and push to S3. So
Okay.
there's no overlap as such, and because otherwise it will be actually terribly inefficient,
Yeah.
as you rightly pointed out.
Yeah. That makes sense. But then it creates a new problem, right? So I have services that are really like spammy logs and a lot of workload. But then there are services who are like really small in terms of workload. They really log like efficiently or really less. Do I fear of like creating a file that is really small on S3 for those services and really large for, services that are really high volume?
Yes, so that might happen. So basically, in some cases, in some data sets, Parquet files can be very big. In
Hmm.
some cases, for other data sets, Parquet files are smaller. But from a operational perspective, that doesn't bother the user, right? So as
Yeah.
long as it's a Parquet file, compressed format, columnar, you're very easily able to grep through the file to find stuff that you need. File sizes as such, as long as it's more than a smaller
Yeah.
or a basic threshold,
Yeah.
doesn't really bother the user too much.
Fair enough. Since we have talked about ingestion and the failure modes as well, now let's say my reads are slow and I want to create index. How do I create index? Is it like the general SQL create index and on this data set, and what does the indexer do when it gets this kind of request?
So basically, it's not like via SQL as such. It's basically a new simple interface on the UI that lets you, let's say, choose a data set first of all. Once
Mm-hmm.
you choose the data set, you are prompted to choose a duration. So you can say that I want a rolling index, which is basically give me the latest 5 days or latest
Mm-hmm.
10 days. Or it can be a static index, which is, let's say, give me 10 p.m. 5th January to 12 p.m. 7th January. So it can be a static index or it can be a rolling index. And let's say you chose a static index. The moment you choose the time range and choose the data set, and set create, basically the indexer node starts reading streaming the Parquet file for that range, starts creating an index, and this
Mm-hmm.
indexer is basically sort of based on the Lucene architecture, inverted index, standard stuff, right? But it starts creating that index and then source that index data on S3 again,
Mm-hmm.
but in a separate prefix. So now you have a separate index prefix where again it's organized with data sets and timestamps, but now this contains the index data. So this is the standard flow. Basically,
Okay.
you choose that what kind of index, what duration. But and coming back to this thing, right? So you have static index. We talked about the static index. For dynamic index, basically you choose just the duration, and the end date is always, or end time is always now, and start time is moving. So every day the indexer actually looks at older data, removes the older data, and then uh, at the time of ingestion also keeps creating the index. So the moment Parquet file goes inside the S3 bucket, indexer is able to pick that file and create the index for that.
Okay, perfect. So I think we have covered a lot of ground, and we have talked about the ingestion path, the topology, and how architecture looks like. We've talked about the optimization, indexing, the read path, how UI is supported, why SQL is supported. So it's a lot of information. So let's talk about what currently you're working on and what's coming in the future when it comes to Parsable.
So I think one of the uh, core aspects that you just cannot ignore now is AI, right? So how can you supercharge the SRE workflows, the DevOps workflows using AI, especially in the
Mhm.
context of observability? So that is one area we are really actively working on.
Mhm.
We are integrating with bunch of models to see actually can we, for example, predict the flows or the data ingestion. Can we predict that there's some anomaly going to happen? And this has been possible using machine learning for a while, but foundational models actually give you a certain new angle. So now you don't have to keep training your ML model for every few days to actually get useful information. Foundation models are much better at predicting stuff, and they can actually detect anomalies a little better. So that is one angle we are actively working on. The other very important angle, which comes from the signal to noise problem that we spoke about early on,
Yeah.
is there's just so much data, and you don't even know sometimes what you're really looking for. So summarization of log data, for example, is going to be very helpful to actually help debug stuff quickly. So you can
Mhm.
actually just select a time range, select a duration, select a data set, and just let AI summarize all the data for you. Of course, it involves technical challenges. How do you manage the context window? How do you manage, the cost of summarization and stuff? But summarization is one of the other interesting areas. Finally, visualization of data also. So when you actually look at dashboards, when you look at certain visuals of your data, it helps you uh, understand what's going on. But how do you start? Where do you start?
Yeah.
So models can actually help you sort of ensure that you start with something which is useful, and then you evolve as you go. So the other angle that we are focused on is how you can visualize stuff using models. So this is where we are actively thinking about, because on the core database or the core observability system, it's rock solid, and now it's the time to ensure how do we actually make AI work for this use case.
Okay, fair enough. And that's a very interesting area to work on because AI can do a lot of stuff for reducing the mean time to resolve an incident, and finding issues early on, finding anomalies as you mentioned. And I see a lot of opportunities in that space. So any development in that area is really interesting and really powerful. Um, how can our viewers try out Parsable? What should they do next, and how can they contribute?
So the core repo is open source. It's on GitHub, Parsable HQ/Parsable. So if you want to like look at the project, understand how it works, feel free to go to the repo, understand, take a look at the README, at the contribution guide and stuff. If you just want to try it out, simple Docker image or a single binary that you can actually run on your machine, ingest data quickly, look at the UI, see how you can use it in your workflows. And of course, we are always open for any sort of feedback that once you use the product, you have some ideas. Okay, why this is like that, and why this is not like that. So any sort of feedback is of course more than welcome. We are also on Slack. uh, uh, you can actually join the Slack community, talk to us, help us improve the product, use the product, and it just helps us sort of understand what are the workflows that we can further solve for. So those kind of join the community, help us, and also use the product. So it gets better. So that's, I think that's one way to get involved.
Perfect. Well, thanks a lot, Nitish, for sharing all the insights, sharing about how Parsable works and the future advancements that you're looking at. For the viewers, I'm going to attach all the links and the Slack community, the open source project, and please try it out. Try out the binary. It's easy to get started when you have a binary. If you like it, give it a star on GitHub. And if you like this episode, hit the like button, subscribe to the channel, and check out all the episodes if you have missed them, and learn about databases, distributed systems, and all the amazing things we have been doing in this industry. So thanks again, and until the next episode.
Thank you so much for having me, KV. It was great chatting with you, and I hope this was useful.